Good morning. Today we are going to concentrate on the lateral stability. If you remember, for the longitudinal stability, we said that the longitudinal response of a helicopter disturbed from a forward flight condition by a vertical gust is made up by a short period response, which is an incidence adjustment, which is followed by a longer period, usually unstable oscillation at constant incidence, and that is the phugoid. Today we are going to concentrate further on the lateral stability. The first mode which comes into discussion is the Dutch roll, or the so-called lateral phugoid. The Dutch roll is an oscillatory combination between roll and yaw motion. The name of Dutch roll comes because of the similarity to an ice skating figure of Dutch skater. The Dutch roll may be described as a yaw and left to the right, followed by a recovery towards an equilibrium condition, then an overshooting of this condition and a yaw to the roll and left, and then back to the equilibrium attitude, and so on. The typical period of this motion is between 3 and 15 seconds. In this mode, usually the roll motion, it can be neglected, so I neglect the derivative np, and in this way we can consider only the combination of the roll and of the lateral velocity. We can find the Dutch roll modes. Usually the NP derivative, so the variation of the N moment, that is the yaw moment with respect when I give a roll perturbation, and couples the roll and the yaw. If the NP is smaller than 0, is destabilizing the motion. Dutch roll is often described as an irritating mode as it interferes with the pilot's ability to hold the trim, and it causes the aircraft to squirrel around the gusty condition, upsetting the passengers. Usually, therefore, we need a certain design criteria for the Dutch roll damping. So we need flying qualities criteria to stabilize this mode. I will come later to the definition of flying qualities and what that means. For example, the occurring of the unstable Dutch roll in a case of the helicopter bulk of BK117 was done by installing vertical surfaces. Usually the dihedral, it also produces a beneficial rolling moment if there is an inadvertent side slip motion. Here is that you see how it was improved the Dutch roll at the BK117. You see the Dutch roll mode damping ratio as a function of the true airspeed. And you see that in the initial design, that as the forward speed was increasing, the roll mode damping, the Dutch roll mode damping was decreasing. Therefore, end plates design were added to the BK117, and you see the improvement in the roll damping. This is actually an example of designing for flying qualities. How does Dutch roll stability affect the pilot control? If we have low stability, we will have large roll, yaw, side slip oscillations in gusty conditions. This is very uncomfortable for passengers, and it involves a high workload for the pilot keeping the track. If we have a too high stability, it will cause a large side slip, which is building up following a roll control input. actually an effect of the weak spiral mode stability. So actually you see that stability and maneuverability involves contradictory design requirements which need a compromise. So we not too little stability, but either not too much stability. We have also here a lateral stability map. One can represent the dihedral effect. If you remember, dihedral effect from the fixed wing is the amount of roll moment produced per degree of side slip. So a positive dihedral effect corresponds to a left rolling moment with a right side slip. And if you represent the directional stability, the positive directional stability means a right yawing moment with a right side slip. You can see again here that there are regions which are unstable and regions which are stable. For example, our helicopter, it has the Dutch roll. This in a basic helicopter, it was stable. You see that if you increase the directional stability, you move in this map actually to a spiral dive, and if you increase the dihedral effect, you move to a stable Dutch roll. Therefore, one needs to be attentive to know where it is in this region. Now a different lateral mode, the so-called roll subsidence. Roll subsidence mode, it's simply the damping of rolling motion, and it involves just one equation, which is the damp derivative, the damping of the rolling motion. In helicopter, this is a highly damped mode, and actually the roll subsidence is similar to the pitch subsidence, MQ. Another lateral stability mode is the so-called spiral mode. The spiral mode is inherent to any aircraft. All aircraft trimmed from straight and level flight, if flown stick fix, will spiral. Some of them will spiral dive, and a spiral dive can be fatal. In a spiral mode, you see that involves mostly for a helicopter the yaw motion, and this is again a damped but not highly damped mode. To test for the spiral mode, you have to trim the helicopter in forward flight and initiate a banked turn, so slightly bank the aircraft and add yaw, and then return to the trim. If the helicopter will return to the level flight, it means that it is stable. If the bank angle will increase, it means that it is unstable. Now, if you recall all these lateral modes, and if you recall as well the longitudinal modes, it means that the helicopter stability of free motion, it involves actually a short period pitch oscillations which is heavily damped so that the pilot may not even notice it, and a phugoid oscillation which is actually an exchange of energy between speed and altitude. Also, in lateral mode, it involves a highly damped aperiodic motion, roll motion, the roll subsidence, a weakly damped unstable aperiodic motion, the spiral, and the roll-yaw oscillations, which is often poorly damped, the Dutch roll. Don't forget, in hover, the longitudinal and the lateral modes couple strongly together. And also, as I said, the short period mode, especially in hover, it can be a non-oscillatory mode. Here you see a picture of eigenvalues modes variation with the forward velocity. There are two helicopters. On the left hand side the Puma helicopter, on the right hand side the Lynx helicopter. The difference between them is that Puma corresponds to an articulated helicopter, while Lynx corresponds to an hingeless helicopter. Here you see the eigenvalues, so the damping and the damped frequency of the motion. The phugoid is going from hover to 160 knots, so you see that phugoid is on the right hand side of the graph. So the motion in phugoid, the phugoid, it is an unstable mode. The Dutch roll is unstable in hover, stabilizes somehow and then destabilizes again. You see the pitch, the short period mode. So the short period mode is going from hover and then up to 160 knots, becomes oscillatory, and the damping more or less the same. The roll subsidence mode, going from hover and increasing to the forward flight, and the spiral mode, which is not highly damped and not oscillatory. For the Lynx, you see that the phugoid mode is again unstable. You see again the Dutch roll, which is in this case more stable. You see also that the short period now becomes a pitch subsidence. You see going increasing its damping as I fly faster, and the heave subsidence, which is very little damped. You see the lateral modes, the roll subsidence, and you see also the spiral mode, little damped. Therefore, there is a difference in behavior between an articulated helicopter and an hingeless or bearingless helicopter. This makes the things more complicated with helicopters. Also, the modes usually couple together. I will now shortly discuss on the flying qualities and handling qualities. What are flying qualities? In 1949, Phillips were defining flying qualities as the stability and control characteristics that have an important bearing on the safety of flight and on the pilot's impression of the ease of flying an aircraft in steady flight and maneuvers. What are handling qualities? Cooper and Harper in 1969 gave the most classical definition. Are those qualities or characteristics of an aircraft that govern the ease and precision with which a pilot is able to perform the tasks required in support of an aircraft role. In literature, these terms, flying qualities and handling qualities, are sometimes confused. Actually, between flying qualities, stability and control, and handling qualities, there is a difference. I showed you here what means flying qualities, what means handling qualities. The definition of flying qualities includes actually the stability and control characteristics, and more or less it is a subset. Aircraft handling qualities are a subset of flying qualities which directly relate to pilot opinions. For handling qualities, Cooper and Harper defined a handling qualities rating scale using this format that is given to the pilots. Namely, if a pilot is flying a task and it gives a rating of 1, 2 and 3, it says that we are in a level 1 handling qualities. Level 1 means that the aircraft is satisfactory without improvements. If we are in 4, 5, 6, we are in a level 2 handling qualities. In level 2 handling qualities, we still achieve the adequate performance, and we need anyway that the pilot needs to use compensation in the given controls. At the extreme of level 2 handling qualities, the mission is still flyable, but the pilot has little capacity in sustaining the flight without danger of error. In level 3, 7, 8, 9 and 10, the aircraft is unacceptable as task performance. This level is necessary to describe the aircraft's behavior in emergency condition or following the loss of critical flight systems. Usually, we design for level 1 handling qualities. However, helicopters finally end in the level 2 handling qualities. Remember, for example, the Dutch roll problem. As I said, the Dutch roll, it is an upsetting mode for the pilot and for the passengers. There have been defined the handling qualities levels for the Dutch roll stability in a handling quality map. You see here the damping in the roll, Dutch roll, and the damped frequency. You see the level 1, the level 2, and the level 3. Here are the BO-105. BO-105 helicopter. One is in theory, you see in this range, and this was the BO-105 in flight. The Puma SA330, you see the Puma SA330 in flight. In theory it was level 2, in flight it was between level 2 and level 3. And you see the Apache H64, which is in theory predicted level 1, in flight it is a level 2. Therefore, we need this criteria to describe how the pilot how easy the pilot is flying the task. I ended today the course on stability and control, and this ends the helicopter stability.